Thanks for joining us. Neuromorphic computing is one of the most exciting areas of computer architecture today. Mike Davies, director of Intel's Neuromorphic Lab, joins us. If you haven't already seen his videos on the basics of neuromorphic computing, you can find those in the description below. Mike, thanks for joining us. So how did you get into doing neuromorphic computing at Intel?
Oh, well, in some ways it goes all the way back to when I was in school at Caltech. And Caltech is actually where the modern form of neuromorphic computing originated with Carver Mead. And I had the fortune to take Carver Mead's class, but ultimately I went a different path. So along with some other students at Caltech, we started a company called Fulcrum Microsystems, where we were taking the research in asynchronous design from Caltech and applying that to Ethernet switches. And 10, 11 years later, Intel acquired that company, which brought us into Intel with this asynchronous design methodology, best in the industry. And it happens to be the tool that you need to do neuromorphic chip design. So when the circumstances transpired to where Intel Labs wanted to launch a neuromorphic research program, we happened to have the best tool available for the job. So that is what brought me into Intel Labs, that brought my group that had come from Fulcrum, and the rest is history in some sense.
So in terms of the asynchronous part of the design, what is the benefit that you get from asynchronous in neuromorphic computing?
Well, actually, we touch on that in the Architecture All Access. Asynchronous circuits are great at exploiting highly sparse activity patterns. So when an asynchronous circuit has nothing to do, when there's no computation that has to be performed, it will be completely idle. It won't consume any power. It only activates and actually consumes power when there's useful computation. There's no clock, in other words, as in a standard synchronous design. So while you don't necessarily have to have asynchronous circuits to implement neuromorphic chips, it's really the right tool for the job, and it brings a lot of extra benefits.
Okay, so that power savings is really powerful, or I should say less powerful when it comes to asynchronous design.
That's right, yeah. It really allows you to translate the theoretical power gains you can get with neuromorphic architecture into realized power gains in the actual silicon.
So tell me about something called INRC.
INRC, that's the Intel Neuromorphic Research Community. So that's a program that we started in 2018 when we launched Loihi. Formally, it's the system for university groups and other research groups around the world to get access to the Loihi hardware. But more generally, we're trying to build a community around this new architecture to solve some of the common problems that we all face, around programming challenges, applications, these kind of things.
Okay, so you get a lot of good feedback, and it's a very collaborative relationship?
Yeah, definitely. We get tons of feedback. We have over 150 groups around the world now using Loihi. We hold workshops a couple times a year, typically, weekly forum where people can join and kind of hear about what the latest developments are. And yeah, ultimately that leads to a lot of really good technical feedback about what's working, what's not with our Loihi chips.
Okay, so Loihi 2 just came out. Mm-hmm. What kind of feedback do you get that goes into developing something like Loihi 2? Does INRC, does that have a big impact on what you develop?
Well, a lot of changes we made in Loihi 2 were pretty directly the result of learnings from that community, that INRC community of researchers. Example is the learning architecture, where we found that although we had kind of the state-of-the-art, best features in our learning architecture in Loihi 1, there's a whole class of emerging learning algorithms that we had weak support for. And that became pretty obvious as people tried to prototype these emerging algorithms onto Loihi 1, and we found limitations. So we addressed that in Loihi 2. Things like the programmability we have in Loihi 2, that's really coming from the observations that all these different groups were pursuing examples that were really stressing the more fixed function, hard-coded aspects of Loihi 1. And rather than try to continue to add more knobs and buttons and extra programmability in a more restricted way, we just went and added an instruction set to the neuron programs.
Okay. I've heard it said that it's easy to create a hardware architecture, but not necessarily so easy to create the software. What is the software story around the Loihi chips?
Yeah, well, this is a particularly daunting problem, I would say, in the neuromorphic space generally, because the hardware architecture itself is still a topic of research. So the very underlying hardware the software would run on is not yet determined, while simultaneously the software is unclear. So it's a chicken and the egg problem. And the way that I look at this is that we're in an iterative exploration process. We have to try something at the architecture level, see what that enables from an algorithmic software perspective, learn from that, iterate it again, and progress in kind of the steepest gradient path in architecture software exploration. But yeah, we're developing software now, putting a lot of effort in that domain. We have a software framework that we've just launched, or 6 months ago anyway, called Lava, which we hope to see adoption across the community as an open source project with permissive licensing. Everybody can work together, port it to their own hardware platforms, and kind of really get some convergence in this field, which is one of the most critical, lacking aspects of neuromorphic software.
Tell me a little bit about Lava and the benefits that you have from it being open source.
So Lava is not necessarily our software framework. So this is an open source project that we've launched about 6 months ago now. We didn't actually even expect to have to do this, but there's a need in the neuromorphic computing space for a single, commonly converged used software framework, and one wasn't developing. We need that in order to be successful with the long-term vision for neuromorphic computing. So we created it, and it needs to be open source. It has to have permissive licensing in order to incentivize everyone in the field, including other commercial chip manufacturers, to use it and to port it to their own platforms and get the maximum amount of researchers behind it, helping to develop it.
Okay, yeah, so that makes a lot of sense to put that out, sort of raise all boats and move the community forward, so to speak.
Exactly. Yeah.
Okay. In terms of the type of data that you're able to get from your INRC participants, what kind of direction do you see in terms of where are the best use cases for something like neuromorphic compute?
Well, I think if you look by the numbers, most of the INRC researchers are interested in robotics. And I'd say that from a fundamental perspective, that's fairly natural, because brains, after all, evolved to control bodies, right? Organisms, right, that move in the world. Now, that's not necessarily going to be the nearest term application, I would say, commercial application of neuromorphic computing. I think for near-term applications, we see a lot of interest in aerospace. So Loihi, for example, was recently launched into space by NASA. That's kind of the perfect match to the strengths and the weaknesses of today's neuromorphic technology, that ultra swap constrained application, or size, weight, power constrained application. A satellite that has to operate on solar power, can't send data down to the cloud, for processing, has to process everything right there, very power limited, and also very latency limited if it's going to be controlling the craft in some way, responding to real world environment.
So do you think that as Loihi starts being adopted commercially, is it going to be at the edge? Is it going to be in the data center? Do you have any insights on that?
I think my feeling, along with most in the field, is that edge is where it will see some adoption first. So this is where the satellite example again, which is so obviously matched to the merits of the technology, robots as well being a clear one a little further out. The cloud, the sort of data center, even supercomputer scale computing does offer some very interesting opportunities, but they're not the nearest term ones. Those will probably be a decade away before they're.
What's Intel's strategy in terms of putting out neuromorphic computing in terms of a commercial product?
Well, we are not trying to rush anything to market, let's put it that way. So we want to be able to scale this technology as a programmable device, just like our processors and our GPUs and FPGAs, that can go into many different end applications. We want a whole ecosystem of developers that really know how to unlock the value of the architecture. That really takes time, especially for something like neuromorphic computing, where we're having to figure out everything from the transistors all the way up to the software, right? So we're not rushing things to market. We see some other players in the ecosystem that are putting products out on the market, and good luck to them. There are, after all, specialized examples that do work today, no question. So some value certainly could be unlocked today. I think for us to commercialize the technology, first, we're probably going to integrate it kind of behind the scenes, so to speak. So in accelerators inside our SoCs, where we don't have to expose the full complexity and uncertainties of the programming model to an external developer community, where we have more, and our OEM partners would have more control over what runs on that. That's probably the fastest path for us. But ultimately, our goal is the big prize. It's a programmable neuromorphic coprocessor that can take an entire subsystem of functionality. So a robot that is walking through the world and responding to sensory input, and moving with agility and grace like a real animal might, for example. So that's our goal, and that same processor to then be able to be applied to an airplane or your laptop, right? So a whole versatile application space in the long term.
Awesome. Well, it's definitely an exciting time to be part of neuromorphic computing. So thank you so much for being here. We'll put more links about Intel's research into neuromorphic computing in the description below. Thanks for joining us.